And this lesson is on page 35 of your unit handout. It is section 2.4, which deals with something called the product rule. And the product rule is used to determine the derivative of a product. So I don't know why on my handout up here or on my screen up here it says apply the quotient rule. Is that what it says on yours? Okay. It should say apply the product rule to determine derivatives and to correctly interpret derivatives. There are certain things in mathematics that are, what's the word? I guess the technical word is commutative. I'll give you an example of something that is commutative. If I ask you to take a product of two things and square it, are you allowed to square each part? Well, yes, you are. There's a reason for that in this particular case. The reason is that xy quantity squared means xy times xy, which means x times y times x times y. And the word commutative is basically a fancy way of saying the order doesn't matter here. So I can take x times y times x times y, or I can take x times y times y, and x times x is x squared, and y times y is y squared. So we are allowed to do this. This is okay. But if I said to you, are we allowed to distribute, for lack of a better way of saying it, that squared into both of these pieces? The answer is a resounding no, right? You know that that's not how you take a sum and square it. So what we can say, you would get the wrong answer because it should be x plus y times x plus y, which is not x squared, y squared, plus y squared. Are you with me on that? Okay. So what we would say is that the square of a product is the same as the product of the squares. The order in which you do those two operations doesn't matter. The square of a product is the same as the product of the squares. But the square of a sum is not the same as the sum of the squares. And what we want to do to begin with here is to explore whether derivatives of products are the same as products of derivatives or not. So this whole lesson is focused on determining the derivative of the product of two functions. I really want you to focus on what this says here. This says d dx of f of x g of x. It's the derivative of a product. This is a product. This is the derivative of the product. Okay. So just by way of an illustration here, if I told you that one of the factors of the function, f of x in this case, is 3x, and the other factor of the function whose product we're finding the derivative of is g of x equals x squared, what's the derivative of the product? So what does that mean? It means we're going to find the derivative with respect to x. And by the way, I always say with respect to x, that really doesn't mean much, but it does become important later, of the product of the functions, which is 3x times x squared. So this is the derivative of 3x cubed. In other words, the product of those two functions is 3x cubed. And we certainly have the ammunition in our weapons that allow us to find the derivative of this. This is equal to 9x squared. So just by picking those two random functions that I chose, the derivative of the product is 9x squared. Are you with me? We're okay with that? Okay, so now the question becomes, that's the derivative of the product. What's the product of the derivatives? Do you see how this is different? This is saying take the derivative of each and multiply them together. So this would be the derivative with respect to x of 3x multiplied by the derivative with respect to x of x squared. Again, think of this that I'm going to kind of highlight in in green. Think of this thing that I'm highlighting in green as being an instruction, an operation. What's it telling you? Differentiate with respect to x. So the derivative with respect to x of 3x is 3, multiplied by the derivative with respect to x of x squared is 2x. So the product of the derivatives is 6x. Based on the results, write a conclusion regarding the derivative of a product. All we can say is that the derivative with respect to x of a product of two functions is not the same as the derivative with respect to x of the first function multiplied by the derivative with respect to x of the second function. It cannot be found that way. There is another way to find it, and we use the product rule. And as I'm standing here, I'm trying to make a decision as to whether I will prove it to you or not. And I think it'll only take a few minutes. So I think it's worthwhile for you to see a proof, although you certainly don't have to write the proof down. The derivative of a product says this. Now I know this because I don't care, even though it's been 6, 8 months since I used, more than that maybe, since I've used this. I know the product rule. I'll never forget it, neither will you. The derivative of the product of two things is found by taking the derivative of the first thing and then multiplying by the second thing, and then adding the first thing multiplied by the derivative of the second. Lots of ways that you could write that. I really don't like this notation, but it's visually, it makes sense to people. I don't like it because I have a hard time pronouncing this. I want to say fg prime of x, but it's the derivative of f of x g of x, and it's equal to f prime of x times g of x plus f of x times g prime of x. Now, I think in your textbook, this author is a little quirky this way. He likes to write this term first. So he likes to write f of x g prime of x plus f prime of x g of x, but the order in which you add them doesn't matter. This is very easy to understand, but it's really sloppy. It's just saying the derivative of fg is f prime g plus fg prime. I hope you understand that what I'm circling could be written this way, could be written this way, could be written this way. There's all kinds of ways that I can write it, and I can switch these two terms around. Since multiplication, the order doesn't matter, and addition, the order doesn't matter. There's lots of ways to write it, but I will always go with the order that I have them on the board. This is the best way to put it. d dx of f of x times g of x is d dx of f of x multiplied by g of x plus f of x multiplied by d dx of g of x. Notice when you compare these with these, do you see that what I've done is I've switched the order of the f prime and the g here? That's because if I write this way, it might be construed that I mean the derivative of the whole thing, but I don't. I mean that. It's kind of like having root x times 4. We would much rather write 4 root x. Anyway, that's the product rule. Derivative of the first times the second plus first times derivative of the second. It's almost a rhythmic thing. So I am going to show you a proof here. The derivative with respect to x of the product of two things. Now, it doesn't really matter what I choose. I am going to choose f of x and g of x. Okay. by definition is the limit as h approaches 0 of this function f of x g of x at x plus h, which would be f of x plus h g of x plus h minus the function itself all over h. So what I am going to do, I'm going to need a little more room here. I've got f of x plus h g of x plus h, and then I have this minus f of x g of x. I'm going to choose to take away f of x plus h g of x and add f of x plus h g of x. Hope I got that right. Pretty sure I do. Why am I doing this? Well, first of all, the stuff that I've added in between those two terms, this amounts to 0, so I haven't changed the value of the expression. Now, why am I doing this? Because somebody far smarter than me hundreds of years ago figured out that if you do this, there's a way to find an answer to this problem. People tried stuff. They tried to figure out, well, how can I find the derivative of a product? And they stumbled on this. This is over h. Well, what I'm going to do now is break this into this over h plus this over h. It's like what I just had. I had a conversation with, I think, Lauren a few minutes ago, that I said if you have 1 over 11 plus 7 over 11, that's equal to 7 plus 1 over 11. You can take two fractions with the same denominator and put them together, so I'm going to rip these apart. So now I have the limit, and this is going to get really a little ugly before it gets nicer, of x plus h g of x plus h minus f of x plus h g of x over h plus f of x plus h g of x minus f of x g of x over h. One of the properties of limits that we learned is that the limit of a sum is the sum of the limits, which means I can take the limit of this piece and add the limit of the second piece. What does that give me? Come on. It gives me the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x plus h, g of x over h, plus the limit as h approaches 0. What I'm doing is I'm distributing that limit operation inside of the brackets of f of x plus h, g of x, minus f of x, g of x. Okay. In the first limit argument, on the top, there is a common denominator of f of x plus h. I'm going to factor that out. Limit as h approaches 0 of f of x plus h times g of x plus h minus g of x all over h. Now I'm factoring that f of x plus h out of the top, but then I can just say, well, it's over 1, and I'm multiplying by whatever's left. So it's still part of the top, but I've moved it away from the top a little bit. This is plus the limit as h approaches 0. How many of you are starting to see where this is going? A little bit. You're starting to see something maybe that's familiar. We have, I'm going to take out now the g of x here. And what will I have left? I will have f of x plus h minus f of x over h. Now, another property of limits that we learned is that, and I don't know if I have it highlighted here. In fact, I probably have them both highlighted here. The limit of a sum is the sum of the limits, but also the limit of a product is the product of the limits. And that means that rather than saying the limit as h approaches 0 of this red thing times this green thing, I can say the limit as h approaches 0 of the red thing multiplied by the limit as h approaches 0 of the green thing plus, I'm going to do the same thing over here. And this proof is a nice proof because all we're doing is using the properties of limits. This first little thing that I did by adding these highlighted terms and subtracting them, you would never think to do that. So now I have a further limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h, am I going to fit, minus f of x over h. Okay, so what is this limit equal to? Well, can I go ahead and put h in here? Sure, obviously I can. And I will get f of x plus 0 times, what is this whole limit equal to? G prime of x. G of x plus h minus g of x over h as a limit is the derivative of g of x. What is this equal to? Well, h isn't even involved, so g of x is almost like a constant in regards to that limit. It's not affected by h. And this, the limit as h approaches 0 of f of x plus h minus f of x all over h is the derivative of the function f. And there's the product rule. Now, the terms may not exactly match in terms of order, right? I like to write this stuff first, and then f of x times g prime of x. But there's a fairly basic proof of the product rule. Any questions with the proof? It's been a long time since I've been in university, but I keep in touch with people who are in university, and I know a couple of profs. This is stuff that they have in the lectures. You'll have a lesson on the product rule, and there'll be 2 examples, and they'll spend most of the class proving the product rule. And the philosophy is that if you understand the proof, you can apply it well. So I'd rather you be mildly to moderately shocked by looking at this here than being absolutely blown out of the water next year and not seeing it prior to that. All right, find the derivative. Now, the first thing to note is this is a product. We are trying to find the derivative with respect to x of 3x minus 2 times 4 minus 3x. Okay, could you multiply that out first to avoid the product rule? Yes. You could say, you know what, I don't want to use the product rule. I'm going to say y equals negative 9x squared. What am I doing here? It's all backwards. 6 and 4 plus 10x minus 8. And you could just differentiate from there using what we learned in the first one. But my response to that is, what are you going to do later when it's that? well, you could multiply it all out, but you'd be nuts. That's not the clinical term for it, but you would be a little bit crazy to multiply that out. So we're going to use the product rule. All we're going to do is say that this is the derivative with respect to x of 3x minus 2 multiplied by 4 minus 3x plus 3x minus 2 multiplied by the derivative with respect to x of 4 minus 3x. Now, a couple of things. That big long set of brackets I have right at the beginning is necessary. Otherwise, it might look like you're taking the derivative of more than you're supposed to be taking the derivative of. This set of brackets is not necessary. The other thing I want to point out to you is what I've just written here is not necessary at all. I'm just explaining what it is we're doing. When you see a question like this, I don't even think you need to write anything I've written. You can go right from here to dy dx equals 3 times 4 minus 3x plus 3x minus 2 times negative 3. Now I get in autopilot and I just do it without thinking too much, but let's break this down. What I did was I looked at the first, which I'm finding right now, and I said the derivative of that is 3, so I wrote 3 down. Then I looked at the second, which is 4 minus 3x, and I wrote times 4 minus 3x. Because the derivative of the product is the derivative of the first times the second, plus the first, so I wrote the first down, and then I multiplied by the derivative of the second. The second is 4 minus 3x with a derivative of negative 3. I hope that you haven't had a lot of time for this to gel, but I hope that you understand whenever you have a derivative of something like 7x, it's equal to 7. So I have 4 minus 3x, the derivative of 4 is 0, the derivative of negative 3x is negative 3. All we have to do now is simplify this. 12 minus 9x minus 9x plus 6. I'm just multiplying out the 3 and the 4 minus 3x and the negative 3 and the 2 and the 3x minus 2. You should double check. I've already double checked it at least once. I think it's okay. So the derivative is equal to negative 18x plus 18, which we certainly don't have to do this, but why not? You're going to have to factor everything later, sooner or later anyway. Any questions with the first one? Yeah. Say again. Yeah, and you know what? In retrospect, I think that's probably this. It really doesn't matter, but I think Aiden's hit the mark here because fewer negatives is better generally. So I tend to factor out negatives, but you're right. They're both equal, but this might be what you would see. G of u, well, it's just a letter, equals 2 root u. So I'm going to write G of u equals 2 u to the half times 3u squared minus 2u minus 3. The way this textbook teaches stuff seems a little out of order to me because if you want to differentiate this, I think it's simpler for you to multiply this through first and avoid the product rule. But you will not be able to avoid the product rule all of the time, which is why we're going to get used to using the product rule with stuff, even though we don't need to use the product rule. So G prime of u is the derivative of the first. So this is the first. which is u to the negative half. Just let that settle in your brain. The derivative with respect to u of 2u to the half is 1u to the negative half. I take that exponent of a half and I multiply it by the 2 in front, which gives me a new coefficient of 1. And then I drop 1 from the exponent. This is d dx of the first. Then I multiply by 3u squared minus 2u minus 3. This is the second. So this is half of the product rule. Derivative of the first times the second. Plus 2u to the half. So this is plus the first times 6u minus 2. This is d dx of the second. And I realize something here. It's actually d du. There's no x. And I want to say, what's the big deal? It doesn't matter. It does matter. It does matter. Will certainly matter later. Now you have to simplify this, and we're going to get into more complicated things to simplify, but if I were you, I would just multiply this all out. So I'm going to multiply u to the negative half times 3u squared, which gives me 3u to the 3 halves. I add the exponents of negative a half and 2. Minus 2u to the half. Again, I'm adding exponents. Negative a half plus 1 is 1 half. And then minus 3u to the half. Multiplying here, you get 12 u to the 3 halves minus 4 u to the half. We've got some like terms. We have u to the 3 halves and u to the 3 halves. We've got 3 and 12, which is a total of 15 u to the 3 halves. We have negative 2u to the half and negative 4u to the half, which is negative 6u to the negative half. Nope, to the half. And we got that pesky negative 3u to the negative half. Are we okay to that point? Always want to look to factor answers. There is a factor of 3. And all of these terms contain u. We factor out the lowest exponent on u. And believe me, had we gone back to the beginning and just multiplied that out first, we would have got the answer really quick, okay? But that's not the point. This will be 5u raised to an exponent, which when added to negative a half gives you 3 halves, which I believe is 2. Minus 2u raised to an exponent, which when added to negative 3 halves gives you a half, and then minus 1. And we're done. I don't know, is that quadratic even factorable? No, it's not. Questions with this example? What's the equation of the tangent to this function at x equals 2? So here, this is great. All that simplifying, we don't have to simplify whatever we get for the derivative because we're just going to put 2 in anyway to find the slope. So the slope will be the value of the derivative at x equals 2, and the point is at 2 comma something. Everybody take a minute here. I'm tired of talking. I just need a little mental break. I want you to put 2 into the function and calculate the y coordinate. Negative 80. So we're going to have y minus negative 80 equals the slope times x minus 2. We just need to figure out the slope. This is our y minus y1 equals slope x minus x1. We just need the slope. So let's find the derivative. So what am I doing here? I'm taking the derivative of the first times the second plus the first times the derivative of the second. I'm just going to stand at the back of the room and take a look at that and see if I've got it right. So the derivative of the first is the derivative of 3x squared minus 2x, which is 6x minus 2, times the second, which is x minus 3x squared, plus the first, which is 3x squared minus 2x, times the derivative of the second. The second is x minus 3x squared. The derivative of x is 1, minus the derivative of 3x squared is 6x. Good. So at x equals 2, the derivative will be equal to, well, that will be 10. I'm just putting 2 in for x. 6 times 2 minus 2. This will be negative 10, I believe. This is 8. And this at 2 is negative 11. But can everybody just confirm those 4 values for those 4 chunks of the derivative? I think so. So we just crunch some numbers here. My God, negative 188. So the slope is negative 188. That is not our final answer, but I don't want to spend class time rearranging that for y or rearranging it for 0. You know, multiply it out and set it equal to 0. The lesson to be learned from this example, number 3, everybody, is if you want to find the value of the derivative, don't simplify. If you tried to simplify this expression first, you run the risk of making a mistake. There's no need to simplify. Just go ahead and put in the value of x. All right, we have one more example. Determine the slope of the tangent to that function at x equals 1. So I want to take a little detour here. I want you to notice that this function is the product of 3 things, not 2. So if I asked you to find the derivative with respect to x of a product of 3 things, then what you would need to do is treat 2 of these as the first and 1 as the second. Now, I'm going to show you a pattern here that we can develop. But if I applied the rule that's the product rule to this, I would get the derivative with respect to x of the first times the second plus the first times the derivative with respect to x of the second. Does that make sense? Okay, but the derivative of AB is the derivative of a product. So this part becomes the derivative of the first times the second plus the first times the derivative of the second, and then we have plus AB times the derivative of C. And I'm missing my, second here, I'm missing my C. I got to be careful here. Let me rewrite this first part. This is the derivative with respect to x of A times B plus A times the derivative with respect to x of B. But it's multiplied by C. The whole thing is multiplied by C. This is what I have in that set of brackets, and it needs to be multiplied by C. What does that tell us? It tells us that this derivative of ABC, I'm going to now multiply this C through, is the derivative of A, then multiplied by B and C, plus A is the derivative of B, multiplied by C, plus A times B, multiplied by the derivative of C. Everybody gets a turn getting differentiated. Take the derivative of the first and multiply by the others. Take the derivative of the second and multiply by the others. Take the derivative of the third and multiply by the others. If it were 4 things multiplied, it would be A prime B C D plus A B prime C D plus A B C prime D plus A B C D prime. So this is going to get messy here. It's going to be long-winded, but again, we're just putting in the number 1 in the end. The derivative of the first is going to be 8x cubed, and then I need to multiply by the other 2. Plus the first times the derivative of the second, and I'm going to double check all my work here, times the third, plus the first times the second times the derivative of the third. So just to help you see this a little better, what I'm highlighting are derivatives of the 3 different pieces. Derivative of the first times the other 2, derivative of the second times the other 2, derivative of the third times the other 2. I'm double checking. There's a lot of numbers and x's here. Does it look okay? Okay, so now you're going to put 1 in. I think this is a case where if you start writing all the substitution, imagine rewriting this and having a 1 every place there's an x. Don't bother. This will be 8 times this will be 1. This is negative 3. Plus, this is negative 1. This is negative 15. This is negative 3. Negative 1, negative 15, negative 3. Plus, this is negative 1. This is 1. This is 2. Similarly, I don't think you want to start writing 1s everywhere, and I don't think you want to start putting it into your calculator all in one shot. I think that's asking for trouble. So I'm putting 1 in for x. I'm just going to walk my way through all 9 of these and check them all. I get 8, I get 1, I get -3. Basically, if you put x equals 1 in, the x's kind of, you can ignore them. -1, -15, -3, -1, 1, and 2. So this product is -24. This product is -45. This product is -2. These are all multiplied, right? -71. The slope of the tangent to this function at x equals 1 is -71. Like most of the lessons, like a lot of the lessons in this course, the final example is something you probably wouldn't see on an exam, but it's something that you would probably maybe see on an assignment or definitely see next year. You know, you'll get a question like this next year. Your prof is not going to preface your assignment by saying use the product rule within the product rule. He or she will just say differentiate this, and you'll have to figure it out. So that's the product rule. Tomorrow we're going to look at, and this is coming really fast. It's like normally you get a day to practice all this stuff, but you don't. Tomorrow we'll look at the quotient rule, and we'll also look at what's called the chain rule, which is the most important rule in differentiating. Thursday, we finish the unit. Man, that doesn't seem right. But we will finish the unit Thursday. And we'll review School Friday for you. We'll review Monday and part of Tuesday. I'll firm up the date for the exam later, okay? So page 92, same thing. Do some questions that you feel are going to get you working at this better and better. Julian, thanks for joining us today. You don't have to hang around until the end of the class, obviously, but if you do, that's fine. And I'm going to fire off an email to you a little bit later tonight and just find out how it's going. So we'll talk to you later.